It's probably hard to believe because we've done a lot of other things with covalent bonds and polar covalent bonds and everything else we've known about bonding, or learned about bonding, I should say. But in a lot of ways, everything we've been doing up to this point has been leading to this point with this thing here, intermolecular forces of attraction, or IMFA. And I'm not sure which one is easier for me to say. Definitely IMFA is shorter to write. But intermolecular forces are really important. And in terms of your interaction with bonds, or how you would how that would affect your daily life, is really going to come down to intermolecular forces of attraction. So it's kind of important for us to understand that. And what it is, it's forces of attraction in between two different molecules. So molecule A, molecule B, there's a little bit of some kind of interaction between those two, or attractive force between those two. And how much attractive force and how strong an attractive force depends on a bunch of things, including the types of bonds and differences in electronegativity and all those other things we've done, including Lewis diagrams for that matter. Now, when I say two different molecules, molecule A and molecule B, they can be the same type of molecule. So a molecule of water with another molecule of water. They can also be different, a molecule of water with a molecule of alcohol or something else like that. And then we're talking the differences, so different physical properties based on whether it's the same kind of molecule or a different molecule. And then we are talking about intermolecular forces, and I want to make sure we understand that part of the terminology, because they're in between two different molecules. A bond is, and we're going to not really talk too much about bonds, even though they do play a role. A bond is the forces that hold a molecule together. So for example, if I'm sharing electrons between two atoms to form a covalent bond, there is a force of attraction between those. We generally draw it as a line to say this line represents two electrons being shared. But those would properly be called intramolecular forces. And if you're not really familiar with that term, don't worry about it, because we're not really going to use it. For us, it's going to be inter, but the important thing is there has to be two molecules. And sometimes I'll just write one, which chemical formula, or one Lewis diagram, and that stands in for many of that kind. So for example, this, if I want to look at the intermolecular forces that this thing is capable of, I need to at least imagine that there are more of those. However, I want to pause here for a minute and kind of give you a visual picture of what I was talking about before. The bond between the carbon and hydrogen is not an intermolecular force. The bond between the carbon and the oxygen is not what I'm talking about today. What I'm talking about right now is if I had another one of those nearby, then the intermolecular force is that there's no line there. I'll sometimes draw dots or a dashed line to say there's a force of attraction from one molecule to another. I can show you a better picture, and I'll show you the thing I like, or tell you the thing I like about this one. But in this one, right, I've got my polar covalent bond between hydrogen and chlorine. You'll notice how it's lined up. So my partial negative charge on the chlorine is lined up with, or attracted to, has an intermolecular force of attraction to the partial positive charge on the hydrogen. And that's going to make sense, right? In the same way that opposite charges attract each other with an ionic bond, the opposite partial charges in a polar covalent bond will attract, not each within the atom, or within the molecule I should say, but to another molecule further down the line. And the thing I like about this picture is where it says weak and strong. So bonds are always much stronger because they are more of a physical connection inside the molecule. We're only talking about intermolecular forces, and if we're going to be disrupting anything, we'll be disrupting the force of attraction between two molecules, and for our purposes right now, never disrupting the forces that hold a molecule together. There's another reason why I want to point that out, but we'll come back to it in a few minutes. So every single particle out there can experience some form of intermolecular force of attraction, and as I mentioned before, this plays a role in physical properties like boiling point, melting point, solubility. For us, our main two are going to be these two, the boiling point and the solubility. So I'll ask you to compare boiling points, in some cases melting points, and I'll also ask you to compare solubilities. Okay. Sometimes those forces are very weak to the point that we really don't notice them, at least not under, let's say, normal temperatures that we experience. And other times, not other times, as I mentioned before, even very strong ones. And again, there's one more thing I want to mention, but I'm going to come back to it in a couple of minutes when I can show you the thing I'm talking about. Now, you don't need to write anything down about here because you're familiar with the three states of matter, but what I want you to do is I want you to think about that in terms of two differences. So for example, I can have water as a solid, I can have water as a liquid, I can have water as a gas, and generally speaking, the thing that changes is the temperature. What is it about temperature that allows that to happen? And I know that in a previous year, you learned about particles moving and pushing each other away and needing more space, but we're going to need to think about that in terms of intermolecular forces of attraction, because that is our melting point, boiling point. I can also have different substances at the same temperature having different states. So I can have, I don't know, at room temperature, I can have iron or copper as a solid, I can have water as a liquid, I can have oxygen as a gas, all at the same temperature. What is it about those substances, those compounds or elements, those materials that in some cases hold the particles together in a solid or not at all in a gas? And the answer is intermolecular forces of attraction. Of course, if you get that as a test question, you need to do a better job of an answer, but really that's what it comes down to. So, working our way through the different forces of attraction. London forces are going to be the weakest, and all of those, all atoms are capable of London forces. And London forces are a bit of a weird thing to try and understand, but I don't think it's that difficult, so we'll see if we can get there. But generally speaking, if a stronger force is possible, we ignore London forces. And what I mean by that is if I ask you to tell me what kind of force these particles can experience, you don't have to list London forces if something else is available, because London forces is always possible. So no bonus points for listing that. If you have a nonpolar molecule, and we need to understand what a nonpolar molecule is, then it is only capable of doing London forces. So if I recognize that it's a nonpolar molecule, then I can say London forces because that's the only possibility I will have. Well, okay, how do these very, very weak forces happen? So nonpolar molecules do not have a partial positive, partial negative zone to them. So how do they happen? Think about it this way. Electrons are always moving, and whenever the electron is over here, it's not over there. And as it continues to move, it's going to be somewhere else, and wherever it is means there's places where it isn't. So if I think about this diagram, and I just focus in on those two outer electrons, when they are there at the top, they're not at the bottom. And when they're at the top, there will be this slight, instantaneous, momentary, very brief area of negative charge, because that's where the electrons are, and elsewhere around that valence orbit, there is an area where there's less electrons, so there's perhaps a partial positive charge. Now if you're thinking, well, that's hardly anything and that can't last very long, you'd be right, which makes London forces very, very weak. And as I move those electrons around, so for example here, if I start looking at how these things are arranged, the electrons of that, say, bottom one, the partial negative charge, I don't want to say it that way, that region of more negative charge, because the electrons are in one spot, means that they are now attracting into the area where those electrons aren't on another atom. But as soon as the electrons move around, that's going to change. So they are very, very weak forces. The same is true for molecules, because even though those are sharing electrons, those electrons are still on the move. And when they are in one spot in the shared pair, they're not somewhere else. Moving on to dipole. Now this one we have to have a more polar covalent bond, because the dipole basically means two poles, partial positive, partial negative, and then the other dipole is a partial positive, partial negative. So if I have a polar compound, then the partial charges are going to line themselves up. Now because that is something that is a little bit more fixed and identifiable, this is the zone that has the partial positive, this is the place that has the partial negative. It's a little bit more, I don't want to use the word permanent, but it's the best one I can think of at this point. So I'm going to draw the molecule like that, but if you think of that previous slide that had a hydrogen and chlorine, hydrogen would be the positive end, chlorine would be the negative end. As they line up, then stronger and more long-lasting forces of attraction can occur. And if it was real molecules, it might do this. It might not form a triangle just because of not bond angles, but just because of how close these particles can get, how much they're on the move, and how strong those forces might be, but it could work this way. Hydrogen bonding. Now this is where I want to come back, or wanted to come back, and remind you the difference between an actual chemical bond and an intermolecular force of attraction. And this is probably one of the worst jobs of naming something in chemistry, and there are many examples of terrible names in chemistry. This is probably my personal vote for worst, because hydrogen bond is not a chemical bond. It is a very strong intermolecular force of attraction, but it is not a chemical bond. It is still an intermolecular force, not an intramolecular force. And all kinds of times people are going to get mixed up because it says bond, but it's not a bond. It has very strict criteria, and if these criteria are not met, hydrogen bonding does not happen. You must have a hydrogen attached to or bonded to a fluorine, oxygen, or nitrogen. So three big electronegative elements with a hydrogen. And then you have to have on the other molecule, on the other nearby, the second molecule, you have to have a hydrogen, a fluorine, an oxygen, or a nitrogen. So to draw the pictures, whether or not these would happen, two of them would work because I have a hydrogen attached to an oxygen and with an oxygen nearby, or I have a hydrogen attached to a fluorine with an oxygen nearby. This bottom one here, if one of those molecules rotated, then I could argue with it, but as it stands, the hydrogen is attached to an oxygen and another different hydrogen is attached to a different nitrogen, attached to a nitrogen, but the oxygen and the nitrogen on the other one is a little bit too far away. We'll make more sense of that because I didn't do a very good job there. Okay, now, as I said, the question of so what, and I kind of hinted at the answers in terms of the solubility and the boiling points, melting points. What if I have a lot of London forces? Yeah, well, London force is very weak, but what if I have a lot of them? Does it then start to play a more important role? You could probably guess what the answer is. And then what happens if I mix, this molecule is able to do dipole-dipole attractions, but the other molecule isn't. It's able to do something else. What happens then? And the answer is, depends. However, at this point, you should be able to, given a pair of molecules, identify the type of intermolecular force of attraction that is in there, and if you, or possible there, and if you only have one molecule, then it means many of those. And then we will eventually be able to do predictions about melting point solubility, and you probably could do some of those already based on intermolecular forces of attraction. But that'll be our class practice. I'll see you then.